Anybody to say the opening prayer for us? I should mention a name. Let me check. Uh, Mr. or Dr. Moses Butchie, can you please say the opening prayer for us? Thank you.
Thank you, Most High God, for this session. Thank you that we've gathered. We have the opportunity to gather together to learn, even as we meet. Holy Spirit, give us understanding that we'll be able to apply what that we are learning in Jesus' name.
Amen. Thank you very much. You are all welcome once again to today's virtual workshop. My name is Esther Obeng, and I'm really excited to be your moderator for today's workshop. So, on the 5th of September, the Pediatric Society of Ghana launched the Research Mentorship Program. Okay, and the aim is to bring on board experienced researchers like our facilitator for today to provide guidance, support, and training for a successful research in our various fields of work. So our facilitator for today has actually been with us for the past few weeks. We've looked at Statistics 101, Part 1. We've looked at Part 2. And today we're going to take on the Part 3. So without wasting much time, I would like to introduce our facilitator. He's in the person of Dr. Edmond Tetenate. He's a senior research fellow at the University of Ghana Medical School. He's a renowned epidemiologist and a biostatistician. He is also a trained biochemist. He has over 20 years experience and records in medical sciences. He is very passionate about making data collection, management, and analysis more efficient and effective, and to provide comprehensive, timely, and accurate research solutions to broad-based health service. So this afternoon, we are ready for Dr. Edmond Tetenate. Dr. Nate, your audience, and audience, your facilitator. Thank you very much.
Thank you very much for the good and brilliant introduction by Esther. So, this is a continuation of the series of lectures I'm giving on statistics. So, we looked at study design. We have looked at various ways of summarizing data. And to be specific, we are talking about descriptive. As I said earlier, anytime you collect data, the first thing you should know or you should do is to describe your data. In doing the description, you find out if there are issues with your data or not. In fact, if you have done your data cleaning very well, your descriptive statistics will go on smoothly. After you have described your data with the use of tables, figures, pictures, or whatever it is, and then you have your numerical aspects, which we talked about central tendency. So you indicate if it is the data type is continuous, you indicate the mean, but if it is continuous and it's not normally distributed, then you have to use the median or you log transform the data, depending on how well you want to use it. Now, after you have done this, we have to also talk about the spread of the data points for a continuous type of data. And we use things like the range, the standard deviation, the variance, and other things. Today, we have finished describing your data. Most research looks for an association to make an inference. So today we are going to talk about inferential statistics. It may look very difficult, or you might have seen the statistician working it out, but it's based on certain principles. It's based on certain principles. We are going to dissect these principles and go on to look about, when we say risks, what does it mean? So, at the end of the session, I expect, you are not students, by the way, I expect us to know what is called estimating parameters and hypothesis testing. When we say p-value, what does it mean? Confidence interval, what does it mean? Then, the more difficult ones, odds ratio, relative risk, the interpretation, and what message do they carry? So, we'll describe the three basic things here, the p-value, which comes from hypothesis testing. Then we talk about relative risks and odds ratio. And we assume that we are talking about two binary variables, although it can be a binary outcome and a variable which not need to be binary. For example, marital status is not binary. So you have married, single, divorced, and widowed. But then the outcome is binary, yes or no. And that's what we are going to talk about using the relative risks and the odds ratio. So the lecture divided into two parts. The first one is what are the core principles? Before you go on to do the various tests, you should know the core principles. Now, what are the core principles? The principles is that you do have a population of diabetic patients attending the diabetic clinic. Good. However, you do want to you have designed your study. And the design of your study, there's no way you can include every member or every patient in the diabetic clinic in your study population. Even if it is possible, the question they will ask is there prudent use of resources, especially in this limited aspect of the area of the globe? So what do? We take a sample from the population. We take a sample from the population. When we take the sample, we expect that sample to be representative of the population. And therefore, things like sample size comes in, the sampling technique comes in. Now, that sample, for example, if you are interested in the mean age of diabetic patients, that sample will have the actual mean age. That is assuming we have done a census of all the diabetic patients. They will come out with a mean age. That mean age will be for the population, and that mean age will be what we call the population parameter. Population parameter, PP. However, when you take a sample from the population, and you analyze the data to come out with the age of that sample, the mean age of that sample. We call it sample statistic. Sample statistic. Now, what we intend to do is to use our sample statistic to infer what the population parameter will be, because, in fact, we have not done the population census. So we are taking a sample from the population, do the analysis on that data, calculate the sample statistic, and use it to infer what the population parameter will be. So with statistical inference, it's about using data analysis to deduce properties of the probability distribution of the population. And there are basically two things we use. Which is deriving estimates and testing hypothesis. Deriving estimates and testing hypothesis. Remember, the assumption is that sample data is from the larger population. You can't draw sample from diabetes clinic to make an inference of the hypertension clinic. No. So the assumption is that sample data or the observed data is from the larger population. So I said there are two approaches. Estimating parameters. And these are things you have seen severally. We are going to look at what they mean. We have what we call the point estimate and then the confidence interval. The second thing is the testing of the hypothesis. And you can test for significant differences between two groups or across groups. So things like chi-square, Mann-Whitney, t-test, ANOVA. ANOVA and t-test is for continuous data. T-test when you have two groups, and analysis of variance when you have 3 or more groups of participants. So for example, you can use the t-test to determine whether the mean age of female in the diabetic clinic is different from the mean age of male in the diabetic clinic. But when it comes to whether the age of those single, those married, those divorced, and those widowed, there are differences. You have to use, it's the same age, continuous variable. You have to use the ANOVA, that is analysis of variance. So when you have 3 or more, you use ANOVA. And even after ANOVA, you have to go through what we call post hoc analysis. If there's a difference, the post hoc analysis will indicate which pair is generating that difference. You can use the Mann-Whitney, which is the non-parametric version of the t-test, because the data is not normally distributed. And we use the chi-square test when we have categorical outcome and categorical exposure. So, for example, in this case, you have diabetes controlled or not controlled as the outcome. And then the exposure is male or female. So we want to check whether there's an association between gender and the controlled diabetes. You may go further to test for association. In this case, you are estimating effect. Chi-square will give you an indication that yes, there's an association. But it will not tell you whether that association, whether male are better controlled of diabetes compared with female. It won't tell you. Of course, for experienced statisticians and epidemiologists, they will know by looking at their proportion and know that the direction is in this way. Apart from knowing the direction, you also want to know the effect. To what extent are males having a better controlled diabetes compared to female? Is it twice or 3 times? Or is 0.5 times? That means the reverse is true. Females have a better control of diabetes than male. All these are what we are calling test of association. That's effect estimates. And we can use relative risk, or what we also call risk ratio. You can get that from the Poisson regression, or you can use the odds ratio, which you can get from the logistic regression. There are others like the prevalence ratio, which we can get from the Poisson regression, the incident rate ratio from Poisson regression, and then the hazard ratio, among others, which we can get from the cost proportional hazard rate regression. Because the cost proportional hazard regression, you are looking at time to event. If you are interested in the time to the outcome event, then use hazard ratio. So let's talk about the estimating parameters. When we talk about point estimate, it gives a single sample statistic as an estimation of the population parameter. So for example, if I say the sample statistic for the mean age of the patient is 52 years, that is a point estimate. That is a point estimate. Now, that point estimate can further be extended to look at what is the confidence interval for this point estimate. But when you talk about point estimate, there's no associated probability about how likely that value is to the population parameter. There's no level of probability associated. It's just a point estimate. The other one is what we call the interval estimate. So instead of giving a single, please hold on. Okay, so instead of giving a simple point estimate, we want to indicate the viability of that estimate in other samples. To what extent can I get that same estimate I gave you in other samples? That is, I'm taking more than one sample. To indicate the spread, to what extent to which, if I'm to do a point estimate in other samples, what will I get? We'll call it an interval estimate. So with the interval estimate, we are indicating a probability of how likely the value will be if we are to do other samples. And that's what we call interval estimate. And there are several interval estimates, but the one we use mostly in health sciences is what we call the confidence interval. Confidence interval. So the confidence interval will give you a range of values to which indicates how likely a point estimate will be in other samples. So confidence interval is an interval estimate, and it is an observed interval that frequently, in this case, I'm not saying always, frequently, you will include the population parameter. So if I gave the confidence interval for the age to be between 48 years to 60 years, what I'm saying is that there is a probability, which I'll come back to it, that frequency, that the population parameter can be found between 48 and 56 years. That's what is called interval estimate. And this particular one, confidence interval. Now, to calculate the confidence interval, use data from a sample, one sample, and then you indicate the confidence level, which is also called confidence coefficient. The level to which you place your confidence in this interval. So I've introduced some few points. Point estimate, interval estimate, and specifically confidence interval. And I'm saying that the confidence interval gives you a range for which we put a probability of getting the population parameter in the confidence interval. And that probability is what I say is a frequently, never always. So the essence of the confidence interval is to estimate an unknown parameter. Remember, the population parameter we don't know. In estimating it, we want to put a precision to that estimate. In addition, to what extent are we confident of that estimate? That level of confidence is also what we call confidence level or coefficient. Confidence coefficient. And as I said, it's the probability that an interval estimate, in this case, the confidence interval, will contain the parameter. Assuming we take several samples and we keep repeating the study. We take several samples and we calculate the mean. Now, this confidence level will have that range of values, will have a lower limit and an upper limit. This lower limit and upper limit are what we call the confidence limit. So a confidence interval will have a confidence limit. That confidence limit can be a lower limit and an upper limit. And before, there can never be a confidence interval without indicating a confidence level. Because you must put in the confidence we have about the results. So, in this diagram, the first one is the point estimate. The second person is saying it will cost between $9,900 and $10,100. And the lady put a confidence interval to it. And the third one increased the confidence interval, said between 7,000 and 13,000. So, just a summary of this. A point estimate will give you a single sample statistic as an estimation of the population parameter. Single as an estimate of what the population parameter will be. An interval estimate will give you a range of values from A to D, which is used to estimate what the population parameter will be. Remember, the level of confidence is never 100%. So we say that this estimate may contain or may not contain the population parameter. If it is never 100%, it means that we put a level of confidence of 95, is maybe around 95% on it. But that gap of 5% means that the population parameter may not be in the confidence interval. But 95% simply means that, can someone calculate the proportion of 19 over 20 for me? (19 over 20). Okay, Charles, 0.95, that's correct. Any other person? 19 over 20.
Yeah, me too. I have 0.95.
Is it Isaac Pi? Thank you. No, so yes, so that's correct. So 95%, 95%, 95%. All that we are saying is, if we take different samples 20 times, in 19 of them, we expect the population parameter to be between what we have gotten. Is that significant or not? Getting the same answer 19 out of 20 times. Is it due to chance? Getting the something 19 out of 20 times, is it due to chance? Statistics is, of course, that is not due to chance. Okay. All right. Thank you, Moses. All right. So a confidence interval of a parameter, which is a form of interval estimate, is just an interval or range of values which is used to estimate the parameter. It is an observed interval which frequently, and that is determined by the confidence level, may include the parameter of interest if the study is repeated. Now, the confidence level refers to the probability that the interval estimate will contain the population parameter. So the level of confidence we put to the interval is what we call the confidence level or the confidence coefficient. It's the same thing. The only difference is that one is a percentage and one is a proportion. Confidence level is always a percentage. So you get 95% confidence level. Its corresponding confidence coefficient will be 0.95. The confidence limits will refer to the ends of the confidence interval, the lower limit and the upper limit. At this stage, we will not go into the mathematics of it. But it's supposed the calculation of the confidence interval is based on what we call the central limit theory. In principle, what it means is that if you have a continuous variable and we take different samples of it, sample 1, 2, 3, 4, 5, 6, maybe 10 samples of the diabetic clinic, and we calculate the age, mean age for each sample, and we draw the frequency distribution for the sample means, that distribution will be normal in nature. Even if the underlying distribution of the data points is not normal. And this is what we call the central limit theory. Only if, one, we take plenty samples, and two, the minimum sample size for each sample is 30 or more. The minimum is 30. And we take their means of all the samples and we draw a frequency distribution, we'll get a normal distribution curve, even if the underlying distribution of the data points is not normal. So we have talked about estimating a parameter. So in some journals, when you put a point estimate, they will write back to you and tell you, put an interval estimate around the point estimate. And in Stata, you can easily do it. It will ask you what distribution you are looking at. It will put a confidence interval around your point estimate. Now, let's go to the second principle. The first principle is estimating a parameter. Point estimate, interval estimate. The second principle is hypothesis testing. Are there any questions at this time before I go to the second principle? Good, let's go on. In hypothesis testing, all that you want to say is to rule out chance as being a plausible explanation for whatever results we have gotten from the experiment or from the study. We want to rule out chance. If, for example, gender is associated with controlled diabetes, is it due to chance? And in hypothesis testing, we want to rule out that possibility that it is due to chance. And this is what it does. It helps us to decide on one of two explanations. Whether the difference between the sample and the population can be explained by sampling error. Or whether the difference between the sample and the population is too large to be explained by sampling error. Therefore, there appears to be a treatment effect. Now, when we say sampling error, there is a population parameter which we don't know. But because we did sampling and we came out with the sample means, the difference between the sample statistic and the population parameter is what we call sampling error. And so far as you are doing sampling, there's a level of sampling error attached to your values. So hypothesis testing is to check whether in saying that there's an association between gender and controlled diabetes, is it due to the fact that we took a sample of the population? Or is it the difference is so much that it can never be due to the fact that you took a sample of the population, but it's due to the fact that there's actually an association between gender and DM. That's what hypothesis testing goes out to do. So what is hypothesis testing? Hypothesis is just a statement, and it is an assumption of the population. So realize I keep using statistic, sample, population, parameter. That's why I think the first lecture I gave you that particular scene. I think I repeated it here. So hypothesis is just a statement you make about a population. And in hypothesis, you are talking about two or more variables. The relationship between two or more variables. Now, the hypothesis can be that the age of male in the diabetes clinic is higher than the age of the female in the diabetes clinic. That is an example of hypothesis testing. Now, or you can even be that male have more controlled diabetes than female. So, in hypothesis testing, we go through a set of procedure. And there are two hypotheses that we test. There are two types, but they are like, let's say, reflections of each other. It's like the bicycle pedal. You pedal the left, you pedal the left pedal. When it goes down, the right one comes up. And when the right one goes down, the left one comes up. And these two are the null hypothesis and then the alternate hypothesis. So can a bicycle be said that both the right pedal and then the left pedal are both up? No. Therefore, either then we test for the null hypothesis and come out to state that one of them is true. True in inverted commas. Therefore, the other is false. False in inverted commas. I will explain why I'm putting them in inverted commas. When we say null hypothesis, simply saying that the word null means nil. There's nothing. Nothing. There's nothing there. So what is saying that male age and female age, there's no difference. No association between gender and controlled diabetes. That is null hypothesis. Nothing. And therefore, the alternate is what we usually believe in. And that's what we go out to test. And the alternate is that male age is different from female age, or gender is associated with controlled diabetes. So what are the steps? There are 7 steps, but these are done for you automatically using the computer. But you have to state your null hypothesis and alternate hypothesis. So for example, in my slide, I want to find out whether there are differences in the prevalence of STD among male and female. So my null hypothesis is that there is no significant difference in the prevalence of STD among male and female. Maybe our population is students attending University of Ghana. Now, no difference. Now, the alternate can be either one tail or two tail, but not both. Now, if it is one tail, then we can make a statement that males do have a higher prevalence of STD compared to females, or females have a higher prevalence, that is one tail. So you are making a categorical statement. The prevalence of males is higher than females. That is one tail. Another version of the one tail is that the prevalence of STD in female is higher than male. That is also one tail. But what most of us go out to do is to go for a two tail. And that two tail is simply saying is that the prevalence of STD is different from that of in males from that of female. That is, it can either be male being more or female being more. In either of this, you are cool with it. So that is called two-tail. And most research going for the two-tail test because we want to see in either way what is there. You then state your desired significance level, which is called the alpha. And that level to which you can put premium to whatever you have done is usually 95%. But in clinical trials, sometimes they go as high as 99%. Then you need to select the appropriate statistical test to do. As I said in my introductory statements, if it's continuous variable and the groups are 2, you can use a t-test. If it's continuous variable and the groups are 3 or more, you can use analysis of variance. If it is a categorical variable, then you can use the chi-square test. So that aspect, that is item 3, don't worry so much about it. There are a lot of textbooks, there are a lot of readings that can tell you which test, the most appropriate test to do. When you see some of us doing it, it's because you have done it routinely. So it has come to stay. But it's not anything extraordinary. Then you determine the numeric value of the test statistic. That's why at the times you were using the books. Then the appropriate table to look for, the T distribution, the chi-square distribution. All this, the computer will do it for you. The aspect which is important from item 3 is item 6 to you. The interpretation or decision you are going to make. Because the system will just give you the values, but you need to put in the interpretation and thereafter your conclusion. The test statistic will lead to the determination of the p-value. The p-value is just probability value. When you hear anybody saying p-value, it's just probability value. So what we are saying is the p-value is just the probability of having observed the data when the null hypothesis is true. I will explain it. It's just the probability. So what's the probability that I've observed this data when there's no association? There are no differences. So if my p-value is 0.04, in layman's language, I would say the probability that there's no association is what? What percentage? Hello? I've calculated my p-value and I'm saying that the p-value is 0.04. And it's just the probability that whatever I've observed is due to what? Chance. Therefore, the null hypothesis is true. You understand? So a probability of 0.04 indicates that the probability that what I've gotten is due to chance is what? 4%. You get it? So if something's probability is due to 4%, is it significant or not? It is significant. You understand? That means it is not due to chance. If the probability is due to 4%, the due to chance is 4%, then the probability that it is not due to chance will be what? I want a response.
96.
Hello, Ima?
96.
96. You get it? The probability that is due to chance is 4. Then the probability that is not due to chance is what? 96%. Now, remember, 19/20 is what? 95%. So if the probability that is not due to chance is 96%, is it significant or not?
Significant.
It is significant. Thank you. So all these p-value plenty is just, this is the explanation. And the p-value you use, remember, you would have determined whether you are going for a one-tail or two-tail test. So this is what we just discussed. When the p-value is less than the chosen alpha, if the confidence level is 95%, then the alpha becomes what? 100 minus 95, which is 5%, and the coefficient becomes 0.05. So when the p-value is less than the 0.05, what we are saying is that there is less than 0.05 probability that is due to chance. If it is very small percentage probability that is due to chance, therefore what do? We reject the null hypothesis. And therefore we rule out chance. We cancel chance as being the reason why we are seeing the difference. We cancel it out. And when we cancel chance out, what we say is that we reject the null hypothesis. We reject the null hypothesis. Indirectly, what we are saying is the alternative hypothesis is true. But we don't say that because our testing is for the null hypothesis. So we say we reject the null hypothesis. On the other hand, when the probability due to chance is greater than our alpha is 95%, therefore 0.05. The p-value you got was 0.22. That is greater than our alpha. What you are saying is 22% probability that what you got is due to chance. If 22% is due to chance, then it's likely, actually, there's chance. Chance is what we got. And the moment the p-value is greater than the chosen alpha, what we say is we fail to reject. So it's like we fail to reject. If we reject the null hypothesis, it means that there is association. So if you fail to reject, it means that there is what? No association or no significant association. Indirectly, what you are saying is the null hypothesis is what? True. That chance is the reason why we got this value. So this is an example of hypothesis testing. We state the null hypothesis and the alternate hypothesis. And we can state the alternate as a one-tail or two-tail, but not both. So this is an example of a two-tail hypothesis. And the lower one is an example of a one-tail hypothesis. If we put this into the computer, and remember, we are looking at gender, male, female, and STI, present or absent. So automatically, it will tell you we can do a chi-square test, not the chi-square distribution. So this is how our table, how it looks like. And by conversion, as I said during the last lecture, the column headings refers to the outcome, and then the row headings refers to the exposure. So this is what we have. Remember, I also went on to talk about row percentages and column percentages. So in this case, we can write in our test, out of the 100 study participants, out of the 100 male study participants, 25% of them do have STI. Whereas 10.5% out of the 100 study participants, female study participants, do have STI. For someone who is experienced, he can easily see that based on the proportion, male is associated with what? STI, if the p-value is significant. But what happens is that when you do the chi-square test, and this is rare chi-square test, it gave us a p-value of 0.08. 0.008. Now that's 0.008. At 95% confidence level, we can say the p-value is less than the alpha. So this interpretation is saying is that 0.8%, there's a 0.8 probability that the value that the results we got was due to chance. If it is so small, it means that there is a 99.2% that is not due to chance. Therefore, the value we got is true. It's not due to chance. If it's not due to chance, what do? We reject the null hypothesis and indicate that there is an association between gender and the prevalence of what? STI. In this case, a statistically significant association between gender and the prevalence of STI. All right, so this is actually a stated illustration of the chi-square test that you can look at. All these values, they are there. You may not go into. Okay, so the females, they were 95. Out of the 95%, 95 female study participants, 10.5% do have STI. Okay. So this is an example of the chi-square test. Now, remember that you took a sample from the population, and sample data are not completely reliable. In this case, I'm making the statement, they are not completely reliable. There's always a chance or a risk that misleading data will make us to have the hypothesis test to reach a wrong conclusion. There's always a chance. So anytime you make an hypothesis test, remember there's always a probability that a risk that there will be misleading data which will have made it to get a wrong conclusion. And there are two errors involved. The first one is what we call type 1 error, and the second is type 2 error. So, the type 1 error is saying that if there is actually an association, there is actually a difference, there's actually something between two variables, but your study, your sample indicated otherwise, and therefore you concluded that there is no association, you have made a type 1 error. So if in true fact there is an association between gender and STI, but my sample indicated otherwise, then I am said to have made a type 1 error. Erroneously rejecting the null hypothesis, when in actual fact we should have failed to reject it. So what we did was to fail to reject it. But in fact, we should have rejected it. What we have done is to say there is no association, when in actual fact, there is an association. For type 2 error, when you indicate that there is an association, when in actual fact, there is no association. When you say there is no difference, but in true fact, there is a difference, then you have committed a type 2 error. All right, let me take it over again. So a type 1 error, you erroneously reject the null hypothesis and state there is no association. But in actual fact, there is an association. Type 2 error, you erroneously fail to reject the association. You fail to reject the null hypothesis. When in actual fact, you should have rejected it. So these are the two types of error we have. And we put some premium in this type of error. The type 1 error and the type 2 error. So, if a clinician tells a man that you are pregnant, what do you think what type of error do you think the person has committed? Type 1 error. You are making an emphatic statement that there is an association, that the person is pregnant. I have some messages for it. Good. And the other one is, if you tell a person that you are not pregnant, when you are seeing the baby bump, then you are making a type 2 error. For those who are new to this, in the beginning, it's a bit easy. It's like you may not understand it, but with time, you get it. Don't worry about that. It's it's like that. So for those who are new to this, don't worry so much. It's very usual. The difference between a type 1 error and a type 2 error. So between this type 1 and type 2, which do you think is more of an error? Committed by the clinician.
Type 1.
I think type 1.
Type 1, good. Type 1. My mate will say he is good with the example of giving a patient a bad medicine as compared with not giving a patient a good medicine. He's very good in using that example, that this medicine does not work and you give it to the patient, as compared with you didn't prescribe a good medicine to a patient because you think it will not work. Which of these two errors is very bad?
Even the patient one, that wouldn't work.
Hello? Hello, I'm listening.
Please, the question again.
Giving a patient a bad medicine, the medicine doesn't work and you give it to the patient. And not giving a patient a good medicine because you think it doesn't work. Which one is more of an error?
Giving a bad medicine.
Giving a bad medicine. Good. Giving a bad medicine. Because you see, with a type 2 error, you would have prescribed another medicine which you think it works. Or the patient could have gone elsewhere for a prescription. But when you give the patient a bad medicine, you have denied the patient from taking any other medicine. So that is what? Very serious. So we have made talks about hypothesis testing. Now, hypothesis testing will give you a p-value. You use the p-value to make an inference, and that inference will lead us to a conclusion. But we need to go further to understand what the risks involved. What about risks in health research? What are we talking about? So in health research, risks are estimates which describe the amount of risks involved with a particular exposure. So we can say thank you. So we can say the risks of what do we call it? Lung cancer is high among those who smoke cigarettes. And risks are part of our daily lives. We use it to communicate a lot in our daily life. But you see, risks is not certainty. It is not certainty. But there is a risk associated with the outcome if you have this exposure. And we have a lot of studies which publish risks. And these risks are very important when it comes to clinical decision making for both the patient and then the practitioners. Therefore, it's very important to have a very clear understanding of the various risk measures, when to use them, how to interpret them. For example, two readers may interpret and communicate risks in different ways based on their understanding. And I got this example from the net about a paper which was published, and two newspapers read the same paper and they published something differently. It was about the risks of body weight and death. One newspaper said adding pounds, that's adding weight as the years pass, increases death risk. Study finds. The other paper said study shows obesity poses less of a risk than thoughts. They read the same paper, they may come out with different interpretation. So we may rely on others when we rely on others to summarize result studies, we may be faced with conflicting results. And that depends on the writer's skill and perspective. So it is important that when we review papers, we should understand the estimates they are putting in there. So in inferential statistics, we may just go beyond knowing if there's an association or not. That is the hypothesis testing. We want to go beyond that and look at the direction of the association. And that's when risk estimate comes in. And the magnitude of the association. So a chi-square test will give you there is an association. But other tests will give you the direction. That is, male gender is associated with STI more than as compared with female. That is direction. And may even go further to say male are 2 times the risk of STI compared with female. That is, that 2 times there is what we call effect size. Effect size. That is the magnitude of the association. Now, we can use various tests, and it depends on your data type, your study design, and other things, and come out with what we call the relative risk, the odds ratio, the prevalence ratio, the incident rate ratio, the hazard ratio. It all depends on your study design, your data type, the exposure, the outcome, and other things. So for the benefit of this class, for this lecture, we are going to talk about the relative risks and the odds ratio. I know most papers use these two. When it says relative risk or risk ratio, it's just a measure of association between an exposure to a particular factor and the risk of a certain outcome. So if you divide the word, the phrase relative risks, it is, we are calculating risks, we are calculating the relativity of that risk among the exposed. Now, for a 2x2 contingency table, as we have here, this is a typical example of a 2x2 contingency table. As usual, my outcome, disease present, disease absent. And my exposure, exposure present, exposure absent, or exposed compared with unexposed. This will give us what we call a 2x2. Table, or what we call a contingency table. Good. So if we take a look at this contingency table, if it is arranged like what I've arranged, and it is very important that you look at the arrangement, because sometimes when you do the calculation, based on your arrangement, the value you get becomes the inverse of what actually you wanted to state. So for Instator and other software, you always predict for 1. That is the disease state, which is in here as compared with the non-disease state. So we want to talk about the risks of having the disease, as you see here, as compared with not having the disease. So this is what we call a 2x2 table. And the cells A, B, C, D will have values in them like 20, 25, 30, 75. Real values in them. Now, sometimes you go in there and you put your values out there for your examiner to look at. And you have calculated a relative risk. But the examiner looks at your values and said, you have made an error with this calculation. You who have used computer to do the calculation, the examiner is sitting down there. He's not having anything on his hands, and he said there's an error. How did you get to know? The risks of the disease among the exposed. This is the exposed. This, I hope you can see my cursor, the exposed. What is the risk of the disease among the exposed? That is the disease state divided by the sum of the exposed. What's the proportion of the disease state among the exposed? That is what? A divided by A plus B. Do we all agree?
Yes.
Okay. What is, so the risks of the disease among the exposed, if you are exposed, What's the probability, the proportion that you have the disease? It's A divided by A plus B. Good. What about the proportion of the disease state among the unexposed? That will be what? Who can give me the formula?
Now we C over C plus D.
Thank you. Thank you. So we have the risks of the disease among the exposed and the risks of the disease among the unexposed. So when we say relative risks, it's not anything extraordinary. It's just a relativity. That is all. A over A plus B all over C over C plus D. So the examiner will be there. You have your table in there. We'll take a small paper. Ask for a part to write. We'll just do the calculator. Tell you this value is wrong. You get it. Now, relative risk is always a non-negative number. It can never be negative. And at the fundamental level, what is the interpretation of the relative risk? Assuming the relative risk is 1, what is he saying? What he's saying is that the risk among the exposed is equal to the risk among the unexposed. Is that true? If the IR is equal to 1, it means that the numerator is equal to the denominator. Is that true?
Yes.
So, if the relative risk is equal to 1, if the exposed risk is similar to the unexposed risk, is there an association between exposure and outcome? Both of us have the same risk. Is there an association? No. Thank you,
There
Stephen.
is no association.
No. Thank you. That means there's no association. However, if the relative risk is greater than 1, fundamentally that is telling us that the numerator is bigger than the denominator. Is that correct? Is that correct?
Yes. Yes, that's correct.
Good. So if the numerator is bigger than the denominator, what is saying that the risk among the exposed is higher than the risk among the unexposed. Is that correct?
Yes.
That's
Meaning that the exposed status do have what? A higher risk. Agreed.
yes.
And what about if the relative risk is less than 1, like 0.72? What is it telling us?
Means the denominator is higher than the numerator.
Good. Continue.
And therefore, there is a higher risk of people with unexposed disease.
Thank you. Thank you. Thank you. There's a higher risk of the disease among the unexposed compared with the exposed.
Yes.
Therefore, it's likely the exposure status is what? Protective. Do you get it?
Yes, that makes sense.
It's likely the exposure status is what? Protective. Remember, I spoke about it is not all exposures which are negative. Remember the what vaccination thing we talked about in our earlier lecture. Good. So all that we have said is what is in there. And when we talk about risks, the interpretation, assuming the relative risk is 2.0, it says that the exposed person is twice at risk of having the outcome compared with the unexposed person. Because the exposed person is the numerator and the unexposed person is the what? Denominator. So the denominator is always compared with. So a relative risk of 0.5 would mean that an exposed person is half the risk of having the outcome compared with what? An unexposed what? Person. These values can be converted into percentages, but let's let it remain like this. Those interested, you can look at conversion of relative risks into percentage. And sometimes converting into percentage gives you a better writing. You understand? For those in a clinical field, for your fellowship and other things, where you convert the relative risks into percentage when you are writing your discussion or whatever it is. However, what you have calculated is a point estimate. You may get the point estimate, but it is important you always look at the confidence interval. That confidence interval will see whether the association you are talking about is significant or not. And this is how we calculate the confidence interval. It is not to scare you. The computer will calculate the relative risks automatically with the confidence interval. Now, if the confidence interval, the lower limit to the upper limit, passes through 1. So, for example, a confidence interval of 0.8, and then the upper limit is 2.4. And that confidence interval goes with the point estimate. What it's saying is that the population parameter can as well be between 0.8 to 2.4. Therefore, the population parameter can as well be 1. Do you agree? The lower level is 0.8. The
Yes.
upper level is 2.4. It tells you that the population parameter, what's actually in the truth, can actually be what? 1.0. Because it's ranging from 0.8 to 2.4. So you look at the confidence interval in moving from the lower limit to the upper limit. Do you pass through the number 1.0? If you do, then regardless of the point estimate, there is no association. Do you agree? Do you get it? So you look at the confidence interval, inputting a statistical inference on your point estimate. We have done already to give the interpretation statistically. However, if in moving from the lower limit to the upper limit, you don't cross through the point, the number 1.0, it means that it is statistically significant. So that can be, for the first example, that can be, in this example, that can be for the 2.0, that can be, the confidence interval can be 1.2 to 3.2. Then we can say that this relative risk of 2.0 is statistically significant. However, if the confidence level interval for this relative risk of 2.0 is 0.8 to 2.8, it tells you that this 2.0 is not statistically significant. Similarly, if you have a relative risk of 0.8, 0.5, and the confidence interval is 0.2 to 0.8, it tells you that this 0.5 is statistically significant. However, if the confidence interval is 0.2 to 1.2, it tells you that this 0.5 is not statistically significant. So always look at the confidence interval when you calculate your relative risk or any other risk you will calculate. That will give you the conclusion, the statistical inference you will be making. Now, when we say odds ratio, I don't want to believe, but when I'm teaching my students, these days, not knowing all this football betting they do, they are using odds. So I was there and I heard them say the odds of the odds. I say, hey, now these people, do they understand odds? By the way, football betting, they use Poisson regression, by the way. So let's look at this. In odds ratio, is the same contingency table we talked about, but we use it in a special case when you are dealing with a case control study. So in a case control study, you have to use odds. Sometimes we may use it when we are doing a cross-sectional study. We may report odds. But for case control study, you cannot present relative risks. You have to present what? Odds ratio. So, how is the odds ratio calculated? The odds of having the disease, if you are exposed, is A over B. Odds is A over B. The odds of having the disease, if you are unexposed, is C over D. Therefore, the odds ratio is just the odds of being exposed, of having the disease, and being unexposed and having the disease. So it is what? A over B all over C over D. And when you do the math, you come to what we call AD over BC, which is the diagonal A diagonal to D multiplication all over B divided by what? C. So these are some of the things your people will be doing. People will be doing statistics without a computer. The interpretation is the same, similar to relative risks, the confidence interval, everything. Just that in making conclusion of odds ratio, never use risk. Odds is odds and not risk. So an odds ratio of 2.0 means An exposed person has twice the odds of having the outcome compared with an unexposed person, and not twice the risk. Of course, it goes with its confidence interval, and everything remains. Let's look at Madam Moderator. How many minutes do I have? I think I'm still on time.
Yes, please.
I'm still within time. Okay.
Yes, please.
So let's look at, is there a relationship between relative risk and odds ratio? Let's do mathematics. Relative risk is this, as you see it here. Do you agree with me? My cursor is circling around it. And odds ratio is what? That if you expand this equation, you get AC plus AD all over AC plus BC. Do you agree? Or some of you would like to work it out? All right, so work it out.
We agree.
Good. So work it out and let me sip. Thank you. All right. So what is in this? This color is what? Boys, guys, and colors. This color is green, eh? Is it green? Okay.
Turquoise.
Pardon?
Turquoise.
Hey, okay. You all right. And this is yellow. That one there I know. Okay. What is the difference between this equation and that equation? Look at it well. What is the difference between the two? In the numerator and then in the denominator. In the numerator, what's the difference between the numerator here and the numerator there? Denominator, what's the difference between the entire denominator here and the entire denominator in there? Any suggestion? Any contributor? Oh, no contributor.
So they both have AC as
Added to the numerator
yes, into
and the denominator. Yes, AC. Good. Now, what is A and C?
represents the diseased, either exposed or unexposed.
So A plus C refers to the prevalence of what? The disease, agreed?
Yes, disease, yes.
Those in A and C are those with the disease. Okay. So if you look at this equation, assuming A and C contribute very little to the numerator and the denominator, what do you think will happen to the equation? Maybe AC is 2 or 5 and AD is 200. So it's contributing very little to the numerator. And of course, it will contribute very little to the denominator. what do you think will happen? The numerator year
Relative
will be very close to the numerator year. Agreed.
Yes.
And the denominator year will also be very close to the denominator year. Agreed.
Yes. Yes.
So when the prevalence of the disease is very low, the odds ratio is a good approximation of the relative risk.
Okay.
I'm sure most of you have heard this statement before, but this is what the explanation is. When the prevalence of the disease is very low, the odds ratio is a good approximator of the relative risk. So in summary, we do have hypothesis testing, and it comes with a p-value. You may go further and do test of association, which will come with the estimate and its confidence interval. Now, it is appropriate that these days, when you do the test of association, you also have in there the p-value in the data output. You have the relative risk value, you have the confidence interval, and you have the p-value. And in about 99.9% of the time, if that confidence interval passes through 1, the p-value will not be significant. In that majority of time, if the confidence interval does not pass through 1, it is corroborated by the p-value being significant. But in some cases, rare cases, there's a little conflict between the p-value and the confidence interval. In case you meet this rare case, very, very rare case, we put premium on the confidence interval. And of course, we have type 1 error and type 2 error. Significance p-value, confidence interval. And we have this case study. I want a volunteer to read the first case study. A volunteer, please.
Mr. Okansi, staunch Christian, was accused of assaulting a 15-year-old boy. Despite the facts of the investigation, which indicate a mistaken identity, the jury found him guilty and the judge convicted him of the crime. What type of error was committed by the court? Elaborate on your answer.
Any contribution? There is no association. But you are saying there is an association. There are no association between the boy and the staunch Christian. There's no association between Mr. Okansi and the assault. But you are saying there's an association. The drug cannot cure the illness, but you are saying the drug can cure. What type of error is that?
Type 1 error.
Type 1 error. Wonderful. Thank you. Thank you. Type 1 error. Good. A volunteer to read the second case study. This is the last slide, by the way.
An ex-convict was accused of armed robbery in a neighborhood. All material evidence points to his involvement in the crime. However, the judge/jury acquitted and discharged him based on the evidence of alibi. Type of error was committed by the courts. Elaborate on your answer.
What do you think was the error? Although there's an association between the Atayi and the, what do we call it, the crime, they said there's no association. The judge said there's no association. So that is a type 2 error. Thank you. Thank you, Martin. Now, which of these two errors is worse to be committed by the court? Sentencing an innocent man or acquitting a criminal?
Type 1. Sentencing.
Pardon?
Sentencing an innocent man.
Thank you. Sentencing an innocent man. Because you see, the moment you sentence him and later you realize an error, there's no amount of compensation which can be given out for somebody erroneously put in jail. And you remember, in the recent past, there have been series of compensation in America over convictions against the black population in the 40s, 50s. I'm sure you have heard of those stories. And some of those stories were pathetic. And some of those stories, even the accused were killed. There's no amount of compensation. All that you say is sorry. Any money you give will not compensate the person's time, freedom, if you sentence an innocent man. But you see, if you fail to sentence a criminal, somebody will say crime has no what? Deadline. Is it not? Crime has no deadline. So next time, we can go back and look at the facts and we can call them back. We have seen cases like that in the States where crime committed years back are recalled. It is based on this that the judges make the statement beyond all reasonable words. Can someone conclude for me?
Doubt.
Doubt. Because the judge don't want to commit a type 1 error. The court does not want. So they put so much premium on the type 1 error for you, the prosecutor, to put in your case. It's honor for you to say that, to prove that this person committed this crime before we send them. Because if you commit that error, it is bad. And it's because of this, but I don't think they know what is called by type 1, type 2 error. Most of these things come from us, but they have taken it. But you see, the other thing is because of this, that Amnesty International has been advocating for the repeal of the death sentence. You get it? Because you may convict someone and the person will be killed. And later we realize that the DNA does not match. Or during the analysis of the DNA, there was a swap. What do? You can't resurrect the person. So if the person is actually is in cell there, you can call the person out. And based on some of these things, the seriousness attached to a type 1 error. And in all this that we have talked about, it is statistical significance, but it is not clinical relevance. Something which is not significant may actually reflect the study design rather than the relationship between variables. So there have been papers and arguments about the use of statistical significance and clinical relevance or clinical significance. And this is for us to talk about. But let's know that one child who is able to survive a clear case of rabies, all the symptoms there, the child survive out of 200 may not be statistically significant, but we all know that will be what? Clinically relevant. We want to see what happened. The antibody, we want to know. So out there, know that we talk about statistical significance, but that does not equate to clinical significance or clinical relevance. Thank you very much.
Thank you. Thank you very much, Dr. Nati. Thank you so much for breaking it down for us to really understand it. Please, we'll take some few questions. Kindly raise up your hand, then I'll call you and then you can ask your question. Please, do we have some questions for Dr. Nati?
Hey, so everything I said, you understood it.
They've really understood everything.
Oh, I'm not that a good teacher.
Yes, you are.
Hey.
All right. If there are no, okay.
Yes.
Well, it's a comment. Somebody says wonderful presentation. Yeah. That's from Linda. Okay. So if there are no questions, I would now like to invite Dr. Cosmos Yakubu to the chairman. He is actually the chairman of the Research Promotion Committee of the Pediatric Society of Ghana. Dr. Yakubu, please, if you are on, kindly unmute and share some few words with us. Thank you very much.
Thank you very much, Esther, and thank you everyone for making time to attend this evening's lecture. We are very happy that you have made time to join us for all the series of lectures that we have had. We will be having more lectures and eventually be rolling out the mentorship program where we will assign you to mentors to try to start and then undertake your own research activities. So I thank the presenter for this evening. He has been with us these 3 weeks, and we have benefited very much from his lectures. So we thank you very much, Doc, and to everybody, thank you for attending. Make a date with us again during the next lecture. Thank you all. Okay,
Thank
Esther,
you.
Thank you.
Thank you, Dr. Yakubu. So we would like to end with a closing prayer. So Dr. Moses Botwe, if you don't mind, you started with us. Can you please end with us?
We are grateful, Most High God, for such a wonderful time to learn. Your words say we should study to show ourselves approved. Even as we have gained this knowledge, help us to apply it. In Jesus' name, amen.
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 Thank you all so much. God bless you, Dr. Dati. God bless you so much.
Thank you. Bye-bye.
Thank you.
Bye.
Bye-bye.